All right, welcome back to our unit here on bonding. Today's topic is molecular geometry. Okay, lesson 3 of 3, your objectives are as follows. To become familiar with some basic molecular geometries, to understand the VSEPR, valence shell electron pair repulsion model, and how it affects molecular geometry. Okay, to learn how to determine the molecular geometry of a molecule after drawing its Lewis structure. All right, so for your quick write, when you think of geometry, what kind of angles come to mind? Think in degrees. Okay, electrons have a negative charge. So do you think electrons attract or repel each other when they come close to one another? Do you think Lewis structures represent two-dimensional shapes or three-dimensional shapes, and why? Okay, go ahead and pause this while you do your quick write. I'm going to move on. All right, so the VSEPR model. The geometry or structure of molecules plays a big role in determining their properties. In order to predict molecular structure or geometry, we need to consider the VSEPR model. The main idea around this model is that the geometry or structure of a molecule is determined by repulsion between electron pairs. Okay, so think about this. In other words, electrons repel each other and try to be as far from each other as possible. This determines the structure or arrangement of atoms in a molecule. Lewis dot structures represent the two-dimensional arrangement of valence electrons in a molecule. We use the word structure, though, in another way when we talk about molecular structure or geometry of a molecule. Okay, these structures refer to the three-dimensional arrangement of the atoms in a molecule. Okay, so for your notes, question on the left-hand side, answer on the right-hand side. Go ahead and pause this while you write. I'm going to move on. All right, so VSEPR and molecular geometry. So consider this molecule here. Notice, as the atoms move, the electrons repel each other, and the 180-degree bond angle is maintained. Okay. So with VSEPR, we get a linear-shaped molecule with a 180-degree bond angle. Okay, so a linear, molecular geometry or structure here. Okay, so CO2 is a perfect example of a linear molecule geometry with a 180-degree bond angle. Okay, so linear CO2, notice its structure here. Okay, has a 180-degree bond angle. All right. But what if we added another atom to a linear-shaped molecule? Okay, keep VSEPR in mind. Considering VSEPR, how do you think this will affect the molecular geometry or structure? Okay, so let's add another atom here. Okay, so notice, okay, as a result of VSEPR, electrons from the additional atom repel other atoms, creating a 120-degree bond angle, okay, and we get a trigonal planar molecular geometry or structure. SO3 is a perfect example of a trigonal planar molecular geometry. So before we drew a Lewis structure that looks like this. In reality, we might want to consider drawing something like this, okay, with a 120-degree bond angle. Well, what if we added yet another atom to a trigonal planar shaped molecule, okay? Considering VSEPR, how do you think this will affect the molecular geometry? Well, let's find out here. Okay. Is this correct? If we were living in a 2D world, yes, this would be correct. Okay. However, we live in a three-dimensional world, so the atoms arrange themselves 109.5 degrees apart, creating a tetrahedral molecular geometry. Okay. So methane, CH4, is a perfect example of tetrahedral molecular geometry. Okay. Earlier we may have drawn something like this, but in the future, something like this is probably more realistic because it represents the 3D arrangement, okay, of atoms in a molecule. Okay. Okay, so for your notes, what are the different molecular geometries and bond angles? Okay, go ahead and pause this while you write this table. Okay, I'm going to move on here. All right, so molecular geometry with non-bonding pairs of electrons. So here is a molecule with a tetrahedral molecular geometry, okay? So we just learned about this. So an example of a tetrahedral shaped molecule would be methane here, right? If you recall. But what would happen if we removed an atom? What kind of molecular geometry would we get? Well, let's find out. Let's get rid of an atom here. Okay, so non-bonding pair of electrons still repel other bonding pairs of electrons here. Okay, so these two electrons here still repel these pairs of electrons down here. Okay, so because molecular geometry is based on the positions of the atoms and not electron pairs, we get a trigonal, not planar, but a trigonal pyramidal geometry with a 107-degree bond angle. So an example is ammonia here, NH3. Notice it's not plain, it's not flat, it's kind of a pyramid shaped here. Okay, so an example would be NH3 ammonia. Okay, it has one non-bonding pair of electrons. Here would be its Lewis structure that we drew in the past. And if we were to draw it now, this would probably be more of an accurate representation here, okay, with a 107-degree bond angle. But what would happen if we removed yet another atom? What kind of molecular geometry would we get? Well, let's find out here. So we got rid of another atom. We have another pair of non-bonding pair of electrons here. Okay, so because molecular geometry is based on the positions of the atoms, not electron pairs, we get what's called a bent geometry with a 105-degree bond angle. An example is water. Okay, water has, okay, 3 atoms and 2 non-bonding pairs of electrons here. Remember, these still repel these other electron pairs. So for your notes, what are the different molecular geometries for molecules with non-bonding pairs of electrons around the center atom? Okay, so go ahead and pause this while you write this table. Okay, I'm going to move on. All right, so determining molecular geometry. In order to predict molecular structure or geometry, we need to consider several steps. Okay, so for example, let's use these steps to determine the molecular geometry for CCl4, carbon tetrachloride. So step 1, draw the Lewis structure for the molecule. Okay, and there we have it. Step 2, use VSEPR and arrange the pairs of electrons as far away as possible. So we want to kind of make these bond angles to make them more three-dimensional like and arrange them as far away as possible. And step 3, well, based on the bond angle, okay, and the positions of the atoms and how many atoms and the lone pair of electrons, okay, we can determine the molecular geometry here. So there's no lone pairs of electrons here, so I would probably classify it as tetrahedral. So based on the location of atoms and the fact that there are no lone pairs of electrons around the center atom, carbon tetrachloride has a tetrahedral molecular structure or geometry. All right, so let's look at one more example here and use the steps to determine the molecular geometry for SO2. So let's draw the Lewis structure. Step 1. Okay. Step 2, use VSEPR and arrange the pairs of electrons as far away as possible. So notice we have these 2 non-bonding pairs of electrons here. They're going to repel these other electron pairs here. Okay. So we get a structure that's more realistic. It looks like this. Okay. Now we can determine the molecular structure or geometry based on the positions of the atoms in lone pairs of electrons. Okay, well, based on the positions of the atoms and these lone pair of electrons on the center atom, I would call it a bent molecular geometry. Okay, now it's your turn. Okay, for your notes, real quick, what are the steps for predicting molecular geometry or structure? Okay, go ahead and pause this while you write. I'm going to move on here. All right, so practice here. Determine the molecular geometry for CO2 and determine the molecular geometry for PF3. Okay, go ahead and pause this while you work on these. When you're ready to check your work, hit play. All right, let's see how you did. So step 1, let's draw the Lewis structure. Okay, so hopefully you got something like this. Step 2, let's use VSEPR to arrange the pairs of electrons as far away as possible. Well, there's no electrons around the center atom here. So we're going to maintain a 180-degree bond angle. Okay. So determine molecular structure or geometry based on the positions of the atoms in lone pairs of electrons. Well, it looks linear to me. Okay. So based on the location of atoms and the fact that there are no lone pairs of electrons around the center atom, CO2 has a linear molecular geometry here. Okay. All right, let's move on here to PF3. So draw the Lewis structure for the molecule. Okay. Step 2, use VSEPR to arrange the pairs of electrons as far away as possible. So this lone pair of electrons here will repel these other electron pairs down based on VSEPR. Step 3, determine the molecular structure or geometry based on the positions of the atoms in lone pairs of electrons. Well, we have a lone pair of electrons here. So based on this, okay, based on the locations of the atoms and the fact that a single lone pair of electrons is around the center atom, PF3 has a trigonal pyramidal molecular geometry here. Okay, hopefully you got those right. All right, so summarize. Remember, you can always write your own. Feel free to pause this while you write, and we'll see you next time.